Hello, this is Philip Weiner of the University of Florida. This project is being done as a final project for the course EEL 6509 Wireless Communications. This is a review of turbo equalization. The agenda is as follows. After the introduction, there will be a system description, followed by an evaluation, a review of related work, conclusion, and finally a MATLAB demo. The motivation behind this project is intersymbol interference, which creates unreliable communication channels. As the name suggests, signal distortion is caused by a symbol interfering with other symbols in the signal. Turbo equalization aims to fix this issue by employing classic forward error correction with an iterative decoding and equalization algorithm. Digital equalization is used in DSL circuits, especially at high frequencies, especially in the megahertz range. Turbo equalization was first proposed in a paper by Catherine Douillard in 1995. The original system utilized convolution coding and trellis-based models for decoder and equalizer. The purpose of this study is to analyze the performance of equalization techniques that work in this iterative scheme. From probability theory, we know that conditional probability can be used to create maximum a priori or map rules that estimate symbols based on observations. Turbo equalization uses this concept, but using a map decoder and a map equalizer is not realistic because the computation requirements are too high. The probabilities cycle iteratively until some chosen parameter is satisfied. Now we move to the system description. Let's start with the transmitter. Block A of the transmitter is the encoder. Convolution encoding is used to add redundant information to the input. The new signal length is determined by the code rate. For this study, the code rate was set to 1/2, so k bits turns into 2 times k bits. Here we see a very similar convolution scheme that we saw from the course. These are delay elements. They're assumed to be 0 at the beginning, so that takes away a little bit of the bandwidth of the coding. But there's schemes to get around that. But in this, we assume that they were 0 at the beginning. These are the equations that create the B to K signal coming out of the encoder. Next, we have the interleaver. S-random interleaver works basically by making sure that the bits are, a pair of bits are S indices away from each other. The process is perfectly reversible and is reversed by the receiver. Here's the example of 18 bits with a 3 random interleaver, I believe. That signal goes to the mapper. The mapper is in charge of taking the binary bits and making them into symbols that can be transmitted over the channel. BPSK is what was used in this project. It modulates 0 and 1 to negative and 1 ideally. This is the function that takes care of that. Another example that uses 2 bits at a time is QPSK, and that is like a complex modulation technique. Next is the channel. ISI distortion is represented by a linear time-invariant channel. It has a known impulse response given here. In this expression, this is the impulse response working on the input, this is the output, and N of K represents the independent identically distributed Gaussian white noise. The level of noise added to the system is determined by the signal-to-noise ratio, and there'll be graphs showing over a change of SNR, the BER response to that. Now we move to the receiver. Map decoding is used in all of the receivers tested. It will ultimately perform the bit estimates. A map equalizer will serve as the control, and several soft-in and soft-out equalizers were tested for BER performance. The equalizer outputs the a posteriori probability, LE of x, minus the a priori probability coming in from the decoder. Upon the first iteration, the mean is 0 and the covariance is unity. Here we show several expressions, just general expressions for the probabilities, and this is the bit estimate that the decoder will perform. For exact linear MMSE equalization, the estimators obviously require the covariance and expected value. The expressions below are the matrix representations of the receiving filter coefficients a posteriori probability produced by this receiver. These depend on the convolution matrix, covariance, and expected value. The approximations of this system are as follows. Approximation 1, make the coefficients time invariant and use a recursive algorithm to calculate the coefficients. Second approximation is to let the posterior probability go to infinity. And for this method, the computation requirements will only depend on the transmitter filter, not the receiver filter at all. And here we see that this is an expression for what's coming out of the soft in, soft out equalizer, and this is the energy of the system. The MMSE decision feedback equalization system technically uses two filters, one that handles the feedback of the detected symbols and one that handles equalization, the common equalization that all the other ones do, but it technically has two filters. It can also be simplified by approximations, but they are left out of the study because their performance has already been proven to be inferior to other models. For the evaluation, we start with exit chart analysis. For the results found in the paper, the receiving filter was set at n equals 15 for all equalizers. II and IO represent the input and output information that represent Gaussian distributed likelihood ratios. We find similar performance across the board in the exit chart analysis. For the bit error rate comparison, see this table on the right, which shows the bit error performance for soft in, soft out equalizers over several iterations. Obviously, the map equalizer is going to be the best, but we don't see a large drop-off between the exact linear equalizers and its approximate versions. Even at higher iteration counts, the approximates begin to reach map-level bit error rates. And there was no large difference found in the paper for different code rates. They change it from 1/2 to 2/3 and saw no difference. Here, this table reiterates this point. The lowest SNR when the bit error rate is equal to 0.08 is shown here. There's no large drop-off between the approximate and the regular linear equalizer. Here's the MATLAB simulation that I performed. It goes from 0 to 4 dB, and you can see here it's for a single iteration. You can see here that there's no large difference in the first 4 dB, so that it is supported by what was found in the paper. Comes to complexity, we see a graph here that shows very high requirements for the map equalizer. The amount of multiplications and additions are nearly linear for all of the suboptimal receivers. The second approximation of the linear equalizer only depends on the transmitting filter size. Now on to related work. A similar study was performed on turbo equalizers a few years later. The same basic model was used, but some parameters changed. For example, the convolution code produced 512 bits, and a 16-bit interleaver was used. However, the same MMSE equalization method was used, here showing the performance of BER over 0, 1, 2, and 10 iterations. So a similar study with similar results. In conclusion, turbo equalization provides viable solutions for communication over ISI distorted channels. The first approximation of the MMSE linear equalizer is in the best position between the trade-off between computation requirements and BER performance. The degrees of freedom in these systems make them both very interesting and very vast areas of research. So I got a new appreciation for equalization and its area of research. Here we see the MATLAB function that created the plot that I showed you earlier in this presentation. This represents the highest dB range of signal-to-noise ratio that will be simulated in this function. N is the number of bits, H represents the channel filter, and the capital H is the channel matrix, which is used to create the distortion on the transmitting signal. Moving down, we have the actual beginning of the transmitter, where U is just a random group of bits. It's the original code. And then we use a trellis method to get a 1/2 code rate convolution code. It comes out to 200 bits for this example, and goes to the sRandom interleaver, followed by BPSK. Those are the coefficients for BPSK. H again is the channel matrix, so this is where signal distortion for the ISI channel is introduced, followed by an additional Gaussian noise added to the original signal, depending on the signal-to-noise ratio. Here we calculate sigma, which are going to be required for the receiver. Beginning here, we're starting to initialize the coefficients for the linear equalizer and decision feedback equalizer here. We're just considering the first iteration, so the covariance starts as 1 and the expected value starts as 0. This is the simplest case, but I just wanted to show some differences between the map decoder and map equalizer and the linear equalizer and the decision feedback equalizer. Here we see the actual a posteriori LLRs, the log likelihood ratios outputted by the first one here is the linear equalizer and the second one is the decision feedback. Here's the map decoder, which is the same for all 3 iterations that we're testing here. We get gamma, alpha, beta, and then this is the calculation of the a posteriori coming out of the map decoder. To get bit estimates, we have to subtract this probability minus the what is now be considered a priori probabilities from the the first 2 equalizers that we tested. So let me see where we can show that here. Let's see. Here, this is the a priori probability. Notice it's 0 for the map decoder, for the first for the map equalizer, and these are just these 3 if loops right here are simply the bit estimates. We use that to calculate bit error rate, and this is just a graph of all 3 equalizers and their performance over the 4 dB range of SNR, and we can run it right here. And you can see they're very similar because this is only over a 4 dB range where they're going to be pretty similar, and it's only one iteration. But thank you very much. Have a good day.